Hi friends, in this lecture related to relations, first we will revise the things that we had learned in 11th standard, like Cartesian product of two sets, then relation, then we will come to the definitions of domain and range of the relation, then we will understand what is inverse of a relation, and then we will come to the types of relations on a set, that is void or empty relation, universal relation, identity relation, reflexive relation, symmetric relation, anti-symmetric relation, transitive relation, and equivalence relation. After that, we will solve the questions related to these. So be ready with your pen and notebook to note down the definitions of these relations and then to solve questions with me. Say first we are coming to the Cartesian product of two sets, and Cartesian product of two sets will be defined as the set of all ordered pairs in which first element will belong to first set while the second element of ordered pair will belong to second set. Say we have two sets A 1, 2, 3 and B A B. Then Cartesian product of these two sets will be A cross B, and that will have 3 multiplied by 2, that is 6 elements. So 1A will be the first ordered pair, 1B will be second ordered pair, then third 2A, then 2B, and then 3A, and then 3B. It shows the number of elements in A cross B is equal to number of elements in A multiplied by number of elements in B, that is 6. Now when we come to Cartesian product of set A with itself, then that will be A cross A, and that will have 3 into 3, that is 9 elements, and that say 1 1 1 2 1 3, then 2 1 2 2 2 3, and then 3 1 3 2 3 3, and in it the number of elements, that is n A cross A, will be 3 into 3, that is 9. Now when we come to the relation, then relation from set A to set B, A R B, will be a subset of A cross B. It means relation from set A to set B will be a set of all ordered pairs in which first element belonging to set A is related to the second element belonging to set B by a definite rule. And since in every ordered pair we can see that 1 equal to 1, 1 less than 2, 2 greater than 1, like that, it means in every ordered pair there may be a definite relation between the first and second element. Hence every ordered pair can represent a relation. So the number of relations from set A to set B can be equal to the total number of subsets of A cross B, because every subset of A cross B can represent a relation from A to B. And if number of elements in set A is m, number of elements in set B is n, then number of elements in A cross B will be m into n. So the number of relations from A to B, which is equal to the total number of subsets of A cross B, will be 2 raised to the power m into n. Now when we come to the domain of relation, then domain of relation means the first elements of all the ordered pairs contained by that relation. It means the domain of relation will be either the first set or a subset of first set. It means domain D will be either the set itself or a subset of A. While when we come to the range of relation, then range of relation will be the set of second elements of all ordered pairs contained by that relation. It means R will be a subset of second set, that is B. Either it will be equal to B or will be having a few elements less than B. Now when we come to the inverse of a relation, then if A is related to B, it means if R is a relation from set A to set B, then the relation from set B to set A will be called inverse relation. It means B will be related to A by inverse relation. So if we come to the domain of inverse relation, then range of relation will be the domain of inverse relation, while the domain of relation will be the range of inverse relation. Now when we come to the types of relations on a set, relations on a set means the relations from A to A, and relations from A to A means ARA, and we know that ARA will be the subset of A cross A. So we will define the types of relations on a set, means the relation which will be the subset of A cross A. First we are taking void or empty relation. We know that empty set is a subset of all sets, and relation itself is a subset of A cross B. So empty set will also be a subset of A cross B, and every subset of A cross B is representing a relation. So empty set will also represent a relation. That will be called void or empty relation, and will be represented by phi. Say we are having a set of parallel lines L1, L2, L3, and we define a relation on set A as AB is such that A perpendicular to B and AB belongs to A. Then this relation will have no element, because there will be no ordered pair which is subset of A cross A, in which first line will be perpendicular to second line. Hence this relation will represent a void or empty relation. Now we come to universal relation on set A. Universal relation on set A will be a relation in which every element of set A will be associated or related to any other element of set A. It means universal relation will be equal to Cartesian product of set A on itself. Now identity relation. A relation is said to be identity relation if in the relation every element of set is related to itself only. It means if ARA, where A belongs to A, if only ARA, yani element related to itself only exists in the relation, then the relation is said to be identity relation. And here the word only is important. It means in this relation only the elements will be related to itself. Now we come to the reflexive relation. A relation will be said to be reflexive if it will contain every element associated to itself. It means in reflexive relation also, if A is related to itself, then the relation will be reflexive. Then what is the difference between identity relation and reflexive relation? In reflexive relation, only A related to A is not existing. The other possibilities are also there, A, R, B, A, R, C, like that. But A, R, A, every element should be related to itself also. While identity relation consists of elements related to itself only. So now we come to symmetric relation. A relation is said to be symmetric if A related to B implies B related to A. Say if we are taking a set consisting of parallel lines, then every line will be considered to be parallel to itself. So every line will be associated or related to itself. So relation defined as parallel to will be reflexive relation on the set of parallel lines. And if we come to symmetric relation, then if a line A is parallel to line B, then line B will also be parallel to line A. It means the relation parallel to is symmetric on the set of parallel lines. Now, anti-symmetric relation, if A related to B implies B not related to A. It means ordered pair AB exists in the relation, but BA does not belong to relation. Then we will say that the relation is anti-symmetric. Now, transitive relation, if A related to B and B related to C implies A related to C, then relation will be called transitive relation. Say line A is parallel to B, B is parallel to C, then line A will be parallel to line C. It means the relation parallel to defined on the set of parallel lines will be a transitive relation. Now, when we come to equivalence relation, then if a relation is reflexive as well as symmetric as well as transitive, then we will say that the relation is equivalence. So equivalence relation will be reflexive, symmetric as well as transitive. And since in our example relation parallel to defined on set of parallel lines was reflexive, symmetric and transitive, hence this relation will be an equivalence relation. That is, the relation parallel to defined on this set of parallel lines is an equivalence relation. So whenever we will have to prove that a given relation is equivalence relation, then we will have to prove that the relation is reflexive, it is symmetric and also it is transitive. Then it will be an equivalence relation. Now we will solve two questions to strengthen our understanding related to relations. So first, check relations R and S for reflexivity, symmetry and transitivity. It means we have to check whether the relations R and S defined as in 1 and 2 are reflexive, symmetric and transitive or not. Now we come to the first part of the question, and the first part of the question says that A or B, if B is divisible by A, AB belongs to N. It means in first part the relation is defined that if A is related to B, then this implies B is divisible by A, and A and B both are natural numbers. So if we come to the reflexivity, then every natural number is divisible by itself. Since every natural number is divisible by itself, so every natural number is related to itself, implies the relation is reflexive. Now come to the second thing. In second thing, we have to determine whether the relation is symmetric or not. And for that, say A is related to B, then this will implies that B is divisible by A. But it does not imply that A is divisible by B. For example, 6 is divisible by 3, but 3 is not divisible by 6. So it doesn't imply that A is always divisible by B. So this implies B is not related to A, and this implies relation is not symmetric. When we come to the third thing, that is transitivity, then A related to B implies B divisible by A, and B related to C implies C divisible by B. And if B is divisible by A, C is divisible by B, then this implies C divisible by A. And if C will be divisible by A, then this implies A related to C, and if A related to B and B related to C implies A related to C, then this means the relation is transitive. Now we come to second part of the question, and in second part of the question, relation is defined as L1 as L2 if L1 perpendicular to L2. It means L1 will be related to L2 by relation S if L1 will be perpendicular to L2, where L1 and L2 are straight lines in a plane. Let L be a set of all straight lines in a plane. Then any line L1 related to itself implies L1 perpendicular to L1, and we know that a line cannot be perpendicular to itself. So every line cannot be related to itself. So this implies L1 is not related to L1 with the relation S. So relation is not reflexive. If we come to the symmetry of relation, then L1 related to L2 by relation S implies L1 perpendicular to L2, and if L1 will be perpendicular to L2, then L2 will also be perpendicular to L1, means L2 will be related to L1 by the relation S, and this implies the relation will be symmetric. And now we come to the third, transitivity. L1 related to L2 by relation S implies L1 perpendicular to L2, and L2 related to L3 by relation S implies L2 perpendicular to L3. L1 is perpendicular to L2, L2 is perpendicular to L3, then it means L1 and L3 will not be perpendicular to each other, they will be parallel to each other. So it means L1 is not related to L3 by relation S, and this implies the relation is not transitive. Now we come to the next question. In next question, show that the relation R on set A given by R AB is such that modulus of A minus B is even is an equivalence relation. So first we will show that the relation R defined as AB is such that modulus of A minus B is even is an equivalence relation, where the relation is defined on set A. So first we will have to check whether the relation is reflexive or not, and for that, say an element A of set A is related to itself, and A related to A itself implies modulus of A minus A is even. Modulus of A minus A means 0, and 0 is always an even number. So ARA is true. If ARA is true, then this implies that the relation R is reflexive. Now we will prove that the relation is symmetric, and for that, say A is related to B, then this implies modulus of A minus B is even. And if modulus of A minus B will be even, then we know that the modulus of B minus A will also be even. And if modulus of B minus A will be even, then it means B is related to A. It means for every A related to B, B will also be related to A. And this shows that the relation is symmetric. Now we come to the next thing. We will show that the relation is transitive, and to prove that the relation is transitive, we will say that A is related to B, and this implies that modulus of A minus B is even, while B related to C will implies that modulus of B minus C is even. And if we come to relation between A and C, then we will have to check what are the implications of these two expressions. This implies if A minus B is even, then either A and B both are even or A and B both are odd. Either A and B both even or both odd. Now this also implies either B and C both even or both odd. Now since B is common in both the expressions, so we will consider whether B is even or B is odd. If we take the first case, say B even, when B is even, then modulus of A minus B even implies A is even, and modulus of B minus C even implies that C is even. Why is it so? Because difference of two even numbers will be even, or difference of two odd numbers will be even. Difference of an even and a odd number can never be even. So this implies if A and C both are even, then modulus of A minus C will also be even. And if modulus of A minus C will be even, then it means A will be related to C. So A related to B, B related to C implies A related to C when B is even. Now the second possibility, when B is odd. If B is odd, then A minus B even implies B is odd, then to get the difference even, A should also be odd. A is odd, and modulus of B minus C even implies C is odd, because B being odd, B minus C will be even only if C is odd, and A odd, C odd implies A minus C modulus will be even. And if A minus C modulus will be even, then it means A related to C. Thus, whether B is even or B is odd, A related to B, B related to C will implies that A related to C. And this shows that the relation is transitive. If relation is reflexive, symmetric as well as transitive, so relation is equivalence relation. Now we come to the next parts of the question. In the next part, show that all elements of 1, 3, 5 are related to each other. And in this set, all three elements 1, 3, 5 are odd numbers. And we know that difference of two odd numbers will always be an even number. So 1 minus 1, 0, 3 minus 3, 0, 5 minus 5, 0, all will be even numbers. So we can say that each one of the elements of this set, that is 1, 3, 5, are related to each other. Since now we come to the next parts of the question, and in it we have to show that elements of 1, 3, 5 are related to each other. Related to each other means 1, 3, 5 are related to each other by the relation. Now we come to the second parts of the question, and second part states that show that all elements of 1, 3, 5 are related to each other. 1, 3, 5 related to each other by the relation are defined as AB, such that modulus of A minus B is even. And we know that difference of two odd numbers is always even. So the elements 1, 3, 5 will be related to each other. Now when we come to the next part, all elements of 2, 4 are related to each other, then 2, 4 consists of only two elements, 2 and 4, and both are even, and difference of two even numbers will be an even number. So all elements of 2, 4 will be related to each other. When we come to the last part of the question, that no element of 1, 3, 5 is related to any element of 2, 4, then we know that difference of an even and an odd number is always an odd number. It means is not an even number. So the relation R cannot be defined either from set 1, 3, 5 to 2, 4 or 2, 4 to 1, 3, 5. It means the elements 1, 3, 5 and 2, 4 cannot be related to each other by the given relation R.